Hello, fellows! Welcome back to my channel. First of all, don't forget to subscribe and don't forget to hit the like button so we can reach to 100,000 followers. What we will discuss in today's video. Make sure to listen wisely and enjoy the video. Before that, say hello to our fellows members. Today, we're going to explore an incredibly important concept in both mathematics and chemical engineering, differentiation, and its diverse applications in solving real-world chemical engineering problems. Differentiation, as many of you know, is a cornerstone of calculus, helping us analyze how variables change with respect to one another. In chemical engineering, where we deal with systems that are constantly evolving, differentiation gives us the tools to model, optimize, and control these dynamic processes. A related rate is the rate at which one quantity changes with respect to time. It is determined by its relationship to other quantities that are also changing with respect to time. Why do we use related rates? Actually, we use related rates in calculus to solve real-world problems where two or more quantities are related and changing over time. Related rates help us understand how changes in one quantity affect changes in another, often when time is the independent variable. There's a few steps to solve related rates problem. Here are the steps. Step first. Identify the variables and their relationship. Write an equation. Step 2. Differentiate the equation with respect to time, using implicit differentiation. Step 3. Substitute known values to find the desired rate. It's easy, right?
Now let's take a practical example to apply what we've learned so far. This will help us understand how differentiation can be used to solve real-world problems, especially in the field of chemical engineering. Let's proceed.
Here's the problem statement. We have a beaker with an initial radius of 3 centimeters being heated in a laboratory. Due to thermal expansion, the radius increases at a rate of 0.05 centimeters per second. The task is to calculate the rate at which the area of the beaker is increasing when the radius reaches 3.2 centimeters. This problem is an application of differentiation in chemical engineering and is a great example of related rates. Let's dive into solving it. Let's move on to solving the problem. 1. We assume that r is the radius of the given disk, and a is the area. The formula for the area is a equals pi r squared. Using the chain rule, we get dA dt equals 2 pi r times dr dt 3. Given that the rate of increase of the radius, Dr. per dt, is 0.05 centimeters per second, we substitute the values into the formula. 4. At r equals 3.2 centimeters, the approximate rate of increase in area becomes dA by dt equals 2 pi times 3.2 times 0.05. Simplifying this gives dA by dt approximately equals 0.320 pi centimeters squared per second 5. Therefore, when the radius is 3.2 centimeters, the area is increasing at a rate of approximately 0.320 pi square centimeters per second. This demonstrates how differentiation helps us calculate rates of change in dynamic situations like this one. Let's take a look at the problem statement for this example. Here, we are working with a spherical balloon being inflated in a laboratory. Due to the increase in volume, the radius of the balloon is expanding at a constant rate of 0.1 centimeters per second. Our objective is to find the rate at which the volume of the balloon is increasing when the radius of the balloon is 5 centimeters. This example demonstrates the application of differentiation in chemical engineering, where we use calculus to analyze rates of change in dynamic systems like this one. To solve the problem, we start by understanding that the volume of a sphere depends on its radius. If the radius changes over time, the volume also changes. We need to find out how fast the volume is increasing as the radius grows. To do this, we look at the formula for the volume of a sphere and figure out how it changes over time. This involves focusing on how the radius is growing and how this growth impacts the overall volume. By breaking the relationship down step by step, we find a connection between the rate of change of the radius and the rate of change of the volume. Now that we have the relationship between the changing radius and the changing volume, we use the values given in the problem. We know that the radius is growing at a specific speed and that its size at this moment is given. Using these values, we calculate how quickly the volume is increasing at this specific point in time. In the end, we find that the volume is increasing at a rate of, which is approximately 31.4 cubic centimeters per second. For the conclusion, in chemical engineering, differentiation is a powerful mathematical tool that allows us to analyze and optimize processes, such as determining reaction rates, analyzing heat transfer, and optimizing fluid flow. Differentiation helps us to solve the complex engineering problem. By applying differentiation, we also can improve efficiency, enhance innovation, and drive sustainable solutions in chemical engineering. Differentiation also helps engineers to get accurate numbers to solve real-world problems in the engineering field. For example, differentiation is used to calculate reaction rate in chemical processes. Refer to this slide for a summary of key points and visual highlights. Thank you all for taking the time to listen to our presentation today. We hope it was clear and helped you understand the concept we discussed, especially the step-by-step problem-solving approach. It was a pleasure sharing this with you, and we truly appreciate your attention and interest. If you have any questions or need further clarification, feel free to ask.